So we know how to represent a linear map using a matrix when the map is between two vector spaces of the form Fn and Fm, when they're actually just column vectors. Okay? What I want to do now is completely general. Well, not completely. I'm going to do it in 2 steps again. So I'm first going to start with the situation. So let's say this. Given a linear map T from V to itself. I'm going to start with a simpler situation where T is a map from V to itself. Okay? And then in a couple boards down, we're going to replace this V by a general W. And then it's going to be the most general abstract case. But first, let's start with the map from V to itself. We want to find a matrix A such that in some sense, and we're going to make that precise in a minute, T of V equals A times V. And I'm writing in some sense because V can be a space of polynomials, and then this doesn't make sense. Okay, so we need to first make it make sense and then show how we do it. Okay? By the way, a map from a space to itself is often called a linear operator. If you encounter that terminology, that's usually reserved for maps that go from a space to itself, a linear operator. Okay. So let's start with an example. We're going to take the map from polynomials of degree less than or equal to 3 over R to polynomials of degree less than or equal to 3 over R. Okay? And we're going to take the linear operator that does T of P of X equals P prime of X. Okay? We met this specific example before. We showed that it's in fact a linear transformation, that the sum of the derivatives is the derivative of the sum. Remember that? Okay? We know that the image is in fact in R2, right? Derivatives of polynomials of degree less than or equal to 3 are always of degree less than or equal to 2, but in particular they live in R3, right? Okay? So I want to call the range R3 so that we're in the situation of operators, of T from V to itself. Okay? So do you agree that this is a linear map going from V to V, from the same space to the same space? What it does for a polynomial, it takes its derivative. Good? Okay. I want to represent this by a matrix. Okay? So here is what we do. So choose, and there's a matter of choice here. We're going to see that it depends on the choice. Choose a basis with which you're going to work. A basis for your space V, or in this example, R3 of X. And we're going to choose, naturally, the standard basis. The standard basis is, we're going to call it, let's call it E. We're going to call it E, and E is going to be x cubed, x squared, x, and 1. That's the standard basis for our space. Do you agree? Everybody? And let's give these guys names. This is going to be E1, this is going to be E2, this is going to be E3, and this is going to be E4. The elements of the standard basis. Okay? Okay, so a general polynomial, P of X, a general polynomial in our vector space, in R3 of X, is of the form ax cubed plus bx squared plus cx plus d times 1. right? I'm emphasizing that it's not just plus d, but it's plus d times 1. It's a linear combination of the basis elements, right? So the coefficient vector is p of x with respect to the basis e. Remember this notation? Equals a, b, c, d. A, B, C, D. Do you agree? Okay, so knowing A, B, C, D is knowing the polynomial. All the information about which element we're handling is written in A, B, C, and D. Do you agree? Okay, good. Now, this is what we act on. That's a general element here. What is P prime of x? So if P of x is this, P prime of x is what? We know how to take derivatives, right? So it's 3ax squared plus 2bx plus c times 1. That's P prime. Do you agree? And what is P prime in terms of the coefficient vector? Okay, so I'm a bit out of space, so I'll write it here. P prime of x, its coefficient vector, with respect to the same basis, e, is what?
0, 3a.
0, because there's no x cubed. So it's 0, 3a, 2b, c. Do you agree? Okay, so I should add this and then do this. Good? So the map that sends a polynomial to its derivative, when working in coordinate space, with the coordinate vectors, we're looking for a map that sends A, B, C, D to 0, 3a, 2b, 2c. Okay? And that can be expressed by a matrix. We know how to do that. That's what we discussed in the previous clip. Okay? So let's write that. So we're looking for a matrix such that A times V is P of x, but in the coordinate, we're working with a coordinate vectors. A times A, B, C, D would give us precisely 0, 3a, 2b, and c. This is the matrix that represents that transformation. Good? And I can tell you what A is. A is the matrix 0, 0, 0, 0, 3, 0, 0, 0, 0, 2, 0, 0, and 0, 0, 1, 0. That's the matrix A. Okay? Why? Why? You can decipher it row by row, right? So let's do this. This is A. Why? Because if you take A and multiply it by A, B, C, D, what do you get? Well, you wanted to get a 0 here. So whatever these entries are, when you multiply these entries times A, B, C, D, you want to get 0. So obviously they all have to be 0. You don't want A's there, you don't want B's there, you don't want C's there, and you don't want D's there. That's how I got this row. Clear? How do I get this row? Well, I want to have here 3a. No problem. Take a 3 here and then 0, 0, 0. Right? Good? So do you see how I formed this matrix? It's very easy. Good? So the question is, how do we do it so we're looking for A such that this, here it is. And how do we do it in general? how do we find A? There has to be a systematic way of doing it. We're not just going to play guessing games, and these may be much more complicated in general, and there could be 18,000 of them, right? So how do we do it in general? Okay, so here's the general procedure, but let's give things some names. The matrix. So is it clear? Is what just happened clear? Is it clear that this matrix represents that transformation? In the sense that if you take a vector, a polynomial of degree less than or equal to 3, encoded in terms of its coefficient vector, do A, you get precisely the derivative encoded in terms of its coefficient vector. Good? Is the idea clear? Okay? Okay. So the matrix A that we found is called the matrix representation of T. That's what it's called, and it has notation. Remember that in order to form that matrix, we had to choose a basis, right? The basis we chose was E, and E is how we got these coefficient vectors, and that's what determined what the matrix is going to be. So it's denoted like this. We take T, now T is an operator, or a linear map in general, put it in brackets, just like we took vectors in brackets, and put a little e here to denote which basis it was representing T with respect to. Okay, so that's the notation. And it satisfies, tell me if you agree, that if you take the matrix representing T with respect to the basis E and multiply it by the coefficient vector of a vector V with respect to the same base E, what you get is T of V, again, the coefficient vector with respect to the base E. Okay? Sometimes students freak out when they see this, but there's no reason to freak out. It's really just what we did. This is the matrix A that represents T with respect to the basis we chose. This is the coefficient vector of V, P of x in this case. This is the coefficient vector of T of V, P prime of x in this case. Good?
So it's just a notation.
This is just notation for saying precisely that statement. You take T, T of V equals T of E. But if you want V in coefficients and T of V in coefficients, then T is represented by a matrix with respect to the given basis. Okay? So is everybody not scared of this anymore? Okay? Okay. So how do we find T sub E in general? How do we find the matrix in general? Well, not in general yet. We're still in the realm of a linear operator from a space to itself, from V to V, not yet from V to W. That's going to be in a minute. So how do we find it? So how do we find the matrix representation? So the answer is, in general, so let T from V to V, again, we're thinking still of a linear operator, be a linear operator, a map, a linear map from a space to itself, and let, that's one ingredient, that's the T here, the other ingredient we need is the E, right, the basis, and let E equal E1, E2, up to En be a basis for V. Those are the two ingredients involved. Okay. What did we do? What did we do? So if you think of this, once we're in the coefficient realm, okay, what we did is we took the columns of the images, right? Of the images of the T of the EIs, we called them previously the WIs, and those were the columns of A. Remember that? So that's precisely what I'm going to do. Precisely. But I first have to translate things to coefficients. Okay? So here it goes. Take T of E1. Okay? T of E1 is going to be an element in V again, right? An element in V again. I can call it W1, but the point is that I can write it as a linear combination of these guys, right? So I'm going to write it as a linear combination, whatever T of E1 is, previously called W1, now I'm going to write it as a linear combination of these guys, okay? And the coefficients I'm going to give specific names. So it's going to be A11 times E1 plus A21 times E2 plus dot 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 AN1 times EN. Do you agree? Okay? And the reason I have two indices here, the one in the second coordinate indicates that this is T of E1. And the 1, 2, 3 up to N here indicate which E is A the coefficient of. Okay? Now do T of E2. T of E2 is again some linear combination of the EIs. So it's A1, 2, E1 plus A22, E2 plus dot 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 AN2, En. Okay? So these A11, A21 up to AN1 are precisely the coefficients of T of E1 with respect to the basis E. Do you see that? And what I'm going to do is set them as columns of my matrix A. That's what we did. So let's say that T of En is again some linear combination of these guys. I'm going to call it A1N E1 plus A2N E2 plus ANN EN. It's a square matrix because we're working from a vector space to itself. Okay? And now what I'm going to take, so there's a dot 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 here. Should make them big dot dot dots. So now I have all these coefficients, and remember, these are the coefficients of T of E1. These are the coefficients of T of E2. I want them as columns. Okay, I want them to be the columns of my A. That's how we did it when originally it was a T from Fn to Fm. Remember? So how do I make them columns? If you look at the coefficient matrix here, I want the rows to be columns. I take the transpose. Okay? So take the transpose of the coefficient matrix, of this coefficient matrix. So A is going to be, and the way I labeled them is precisely so they fit well, but in an example, this is going to be an 8, and this is going to be a 3, and this is going to be a 17, and this is going to be a -5, and a pi, and whatever. You just have to remember to do the transpose. Okay? So A is going to be precisely the matrix A1, 1, transpose A2, 1, all the way up to AN1, and then A1, 2, dot, 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 all the way up to A1n, and A22, dot, 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 AN2, A2n, dot, 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 ANN. This is A. This is the A. So we get then A equals this satisfies A is none other than the matrix representation of T with respect to the basis E. Okay? So let's show that this indeed works in the example we just did. We guessed A, right? Back to the example, this was our A, right, over here. This was our A, but we guessed it, right? We said, okay, these are going to be zeros because I want to get a zero here. Let's do the procedure that we just described and see that we indeed end up with this matrix. Okay, so let's do it. Let's do that. So back to the example. So before I erase this, is the in some sense clear now? Okay, the some sense is that it's not going to be T of V equals AV. It's going to be that T of V coefficient vector equals A, which is the representation of T, times V coefficient vector. Okay? Okay, so let's go back to the example and show that we indeed get what we wanted. So back to the example. So the example was the derivative, right? T of P of X is P prime of X. Okay, so what is T of E1? E1 was what? Right? Let's look at the example again. This was our T from R3 to R3 given by T of a polynomial as its derivative. We're on this board, please. Please look here. Thank you. So T of a polynomial is its derivative. Okay? So we chose a basis. This is the basis. Now, according to that procedure that we described, what we have to do is do T to each of the basis elements. So what is T of X cubed? That's E1. T of X cubed is 3x squared. Right? And we want to write that as a linear combination of these guys. Then we want to do T of X squared, which is 2x, and write that as a linear combination of these guys. Let's do that. Okay? So T of E1, E1 is just x cubed. T of x cubed is the derivative. T of x cubed is 3x squared. Right? And we want to write it as a linear combination of the basis. So it's 0x cubed plus 3x squared plus 0x plus 0 times 1. That's writing 3x squared as a linear combination of the basis elements. Okay? T of E2 is T of x squared. T of x squared is 2x. Written as a linear combination, it's 0x cubed plus 0x squared plus 2x plus 0 times 1. Right? T of E3, E3 was x. T of x is, the derivative of x is just 1. That's how T was defined. So it's 0x cubed plus 0x squared plus 0x plus 1 times 1. Right? There's a dot here to indicate that this is a product. There's no mysterious 11 that just showed up. Good? And finally, what is T of E4? Is T of 1. What's the derivative of 1? 0. So it's just 0x cubed plus 0x squared plus 0x plus 0 times 1. Right? And now we take these coefficients and transpose them. So these are the coefficients. These are the coefficients, and we transpose them. So T, the matrix representation of T with respect to the basis E, is indeed the A that we found manually without knowing the algorithm for doing it. So it's, this row is going to become the first column. So it's 0, 3, 0, 0, 0, 0, 2, 0, 0, 0, 0, 1, and 0, 0, 0, 0. Clear? Everybody good? Okay, so this is the idea. This is how we find a matrix representing a transformation with respect to a chosen basis. Okay? This is in the situation where T is a linear operator from V to V. Okay? So now that you're no longer scared of this statement, if you're feeling that you understand what this says, right? You take the coordinate vector of V, the coordinate vector of T of V, and the matrix is the matrix representation. Now we're going to expand this to a map not from V to V, but from V to W in general. Okay? But we're going to do precisely the same idea, precisely the same thing. It's going to be a bit more complicated because we're not going to be able to use the same base E for V and W because they're different spaces. So there's going to be a base E for V here and a different base, call it F, for W, which is going to be here. And T is going to be the matrix representation with respect to those two bases. Okay? So it's going to get slightly more scary, but same idea. Okay? So let's do it. Let's do it. And again, let's start right away with an example. And then we'll write the general statement. And that's going to wrap up this discussion. How matrices are just... So there are... Well, I should say that at the end, but there are two things happening here. One is that we can see that linear transformations can be encoded by matrices, right? And the way to do that is an underlying encoding process of encoding vectors as their coefficient vectors, right? Taking a polynomial, ax cubed plus bx squared plus cx plus d, and encoding it as the vector a, b, c, d. That's the underlying encoding process. And then it gives rise to an encoding process in a higher level of a linear transformation being encoded as a matrix. Do you see that? Okay, beautiful. Okay, so here is an example that's going to lead us to the more general situation of a map from V to W. So we're going to take T from 2 by 2 matrices over the reals to polynomials of degree less than or equal to 2. Now these are two spaces that are different. Okay? You can't take a basis for this and a basis for this and have the same basis. They're different spaces. Okay? And the way T is going to be given is I have to tell you what T does to a matrix, a 2 by 2 matrix, and what it does, it should spit out a polynomial, right? So the polynomial it gives is the following: a plus 2b plus 3c plus 4d times x squared plus 2a minus b plus c x plus 3a minus 2b plus c plus 2d. Do you agree that this is a polynomial of degree less than or equal to 2? Okay? And the first thing you need to do is verify that this is a linear map. Okay? And in fact, if you practiced a bit and you got used to the ideas, you should say right away, of course it's a linear map, because each coordinate in the image is a linear combination of the coordinates of the domain element, right? We said that. Okay, so this is a linear map. Verify that T is linear. Okay, and if you're not sure that you can right away do this verification, that means you have to do it. Okay, that means you still need this practice. Okay, so what we're going to do now is trace the exact same ideas that are here on the board. Let's look over here. When it was the same space, we chose a basis, right? Did T to the basis elements, wrote them as linear combinations of basis elements, and then took the transpose, right? That's what happened here. Okay, now we're going to do the exact same thing, slightly differently. We're going to choose a basis for this. Okay, so let's call it E. E is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, sorry, 0, 0, 1, 0, and 0, 0, 0, 1. This is a basis for our domain space, for M2R. Do you agree? And let's call these guys E1, E2, E3, and E4. Good? For the range space, there's going to be a different basis. Again, we have the liberty to choose it, and since we're just doing an example, let's choose the easiest choice possible. So F is going to be x squared, x, and 1 is a basis for R2 of x. Do you agree? Good? And let's call these guys F1, F2, and F3. Okay? Now what we're going to do, just like before, we're going to do T to each of the basis elements in the domain. T of this guy, T of this guy, T of this guy, and T of this guy. And each one of them we can write as a linear combination of the basis elements of the range. Okay? So I'm going to write it on a separate board because this board is full, but I want to show at least the first one here so you understand what's going on. What is T of E1? E1 is 1, 0, 0, 0. I plug in 1, 0, 0, 0 into T and see what I get. I get 1 times x squared, because these are all zeros, plus 2 times x, plus 3 times 1, right? So T of E1 is 1 times F1 plus 2 times F2 plus 3 times F3. Do you see that? Okay. And likewise, I'm going to do for all the other 3. So let's do that. Everybody with me? Okay. The first time you see this, it looks like, wow, this is so confusing. But in fact, after you do a couple of these, it's just becomes such a standard procedure that you really get used to it. Really. There's nothing tricky going on. Okay? So what do we need to do? We need to do T of E1, T of E2, T of E3, and T of E4. Each one we're going to write as a linear combination of the elements of F, and then take the transpose. That's it. Okay? So what's T of E1? So T of E1 is T of 1, 0, 0, 0. By the definition of T, by the way T is defined, it's 1 times x squared plus 2 times x plus 3 times 1. Do you agree? Right? Look at the formula for T. That's what T does to the matrix 1, 0, 0, 0. And now it's written, let's take our blue again, now it's written as a linear combination of the elements of F. 1 times F1 plus 2 times F2 plus 3 times F3. Do you agree? Okay? So what is t of E2? That's t of 0, 1, 0, 0. And again, you can check what t does. So B is 1, A, C, and D are all 0. And what you get is 2 times x squared minus 1 times x1 minus 2 times 1. Do you agree? Okay? Look at the formula and verify that. And these are my coefficients. Good? Everybody with me? Okay. What is t of E3? That's t of 0, 0, 1, 0. That means, let's look here again. Let's see how we do it. C is 1. A, B, and D are zeros. I'm doing t to it. So I get a 3 here. 3x squared plus 1x plus 1. Right? Let's write it. 3 times x squared plus 1 times x plus 1 times 1. Right? Everybody good? And finally, t of 0, 0, 0, 1, you get 4x squared plus 0 times x plus 2 times 1. I take the coefficients and write the transpose. Okay? So my matrix is going to be, and the way it's denoted is T. And now there are two bases that were involved. The basis E for the domain space and the basis F for the range space. So the way it's denoted is like this, with E here and F here. And it's given by the matrix, and I'm taking the transpose. 1, 2, 3, 4, that's the first row. 1, 2, 3, 4. 2, negative 1, 1, 0. And 3, negative 2, 1, 2. Good? And this satisfies, what does it satisfy? That if you take this matrix, and multiply it by a coordinate vector with respect to the vector E, so that's denoted V, coordinate vector with respect to E, what you get is what T would have done to V, expressed as a coordinate vector in the basis of the range, in F. Now are you freaked out? No. Right? It's precisely what happened. Do you agree? Okay, and now it's completely general. Well, I'm going to write it, I'm going to scare you one bit more and write it instead of x squared, x and 1. I'm going to write f1, f2, f3, but that's it. That's the most general case. Okay? Before I do that, so this was an example. Now I want to write the general statement. But before I do that, do you recognize this matrix? What if I added a 13, 8, 3, 13 here? Would you recognize it? Okay, so this is a matrix let's say we're buddies with. Okay, we've encountered this matrix about 17 times throughout this course so far. So notice what happened here. I somehow managed to construct an example that yields this matrix as the matrix representation of the transformation. So you might ask, wow, how did you do that? That's not this. It's the opposite direction. You had a matrix, okay, you wanted to construct a linear transformation that would somehow have this matrix as its matrix representation. Right? Do you agree that that's the opposite direction? Right? So how did I do that?
You took the matrix and you plugged it into the...
What do you mean plugged it in? How did I know what...
You used it as a linear transformation and found the polynomial that you'd get.
Why polynomial? It's just a matrix.
It could be anything. It doesn't
exactly. Well, all I need for this to be the the representing matrix of some t, I need it to satisfy AV. I need to define t as A times V. So I need to take some space of dimension 4, because this can be multiplied by 4 tuples, right? Do you agree? So this matrix is going to act as a linear transformation on a 4-dimensional space. Now, if I just took R4, that would be too easy, right? I wanted to make it interesting, so I took another 4-dimensional space. I took M2 of R, right? I don't care how it started out as a 4-dimensional space. I know that after I write coefficient vectors, I'm going to get A, B, C, D, and that's what A is going to multiply. Okay? Now, for the range space, what is the result going to be? If I multiply this matrix by a column vector with 4 entries, I'm going to get a column vector with 3 entries. So the range space has to be of dimension 3. So I chose a space of dimension 3. For example, R2 of x, polynomials of degree less than or equal to 2. Okay? And then I don't care that what 3-dimensional space I chose. All I care about is that the coefficient vectors are going to be 3-dimensional. Something times the first basis element, plus something times the second, plus something times the third. Okay? So that's how I found the range space and the domain space. That's how I chose M2 of R and R2 of X. A 4-dimensional space and a 3-dimensional space. That doesn't tell me what the map does. How do I get T to do precisely this? Huh? Right? I'm not done yet. All I said so far was why I needed this to be a 4-dimensional space and this to be a 2-dimensional space. How did I figure out that T is going to do this? Right? How did I know that this was the formula that I need? Ah.
You multiply the basis by...
What basis?
Well, you define the basis for M2R.
Exactly. I chose a basis for this, namely this one. Okay? And I know that I know what I want T of the basis elements to be. Okay? And I know that if once I fix T on basis elements, it fixes the entire linear map. That was a statement from the previous clip, right? When we define T on the EIs, that's it. It determines the map. So I knew that this is what I want. I knew that I wanted T of 1, 0, 0, 0 to be this, because I wanted that to be my first column. And I knew that I wanted T of 0, 1, 0, 0 to be this, because I wanted this to be my second column. Okay? So I knew what I wanted T on the basis elements to be, and once I defined that, T of A, B, C, D is now determined. A, B, C, D is A times this plus B times this plus C times this plus D times this. So T of A, B, C, D is A times this plus B times this plus C times this plus D times this, which is precisely what I defined. Good? Okay. So I'm not going to write everything I just said, because it was really rephrasing ideas that were all out there already. Okay? But if you want, you can rewind and play it again if it was too fast or you didn't absorb everything. But I'm gonna give it as an exercise. I'm going to give it as an exercise. See if you really understood. So homework. Try this. If you can do this, then you understood a lot. Okay? Then you really picked up a lot of ideas. Start with any A. Choose your favorite matrix. Don't choose a 17 by 35 matrix. That would be too long, right? Choose your favorite 3 by 4 or 2 by 3, or choose your favorite matrix and find T, and you have to find what T goes from where to where. Find some T from some V to some W such that such that the matrix representation of T with respect to E and F, where E is a basis for V and F is a basis for W, is the A you started with. If you can do this, okay, which is precisely what I described here, how I did this, how I found a T, a V, and a W such that the representing matrix would be this one. If you can do that, then you really understood this stuff. Okay, then you know what you're doing. Try this. Okay? Okay. So what I want to do now is write this in general. So this was an example. I want to write this statement to generalize it, to make it abstract, and then this is going to be a theorem. Okay? So let's do that. And all the ingredients are on this board. I'm going to modify it very, very lightly. So how do we find T, E, F? Okay, I'm really rephrasing this board. So let T from V to W be a linear, it's no longer a linear operator because it doesn't go from a space to itself, be a linear map. Okay? Everybody with me? What I'm trying to show you is that it's precisely the same idea. That's why I'm not taking the trouble to rewrite it, but rather just modifying it. And let E be a basis for V, but that's not enough now. And I'm going to have to reduce the font slightly. And F equals F1, F2 dot Fm be a basis for W. Now there are two bases, one for the domain and one for the range. Good? Did everybody copy up to here? I'm waiting. Tell me when you're done. Good? Okay. Now I'm going to do T to the EI's, just like here, but they're not going to be linear combination of the EI's. They're going to be something in W, so they're going to be linear combination of the FI's. So it's going to be A11. So I'm going to erase all these little E's. And now T of an EI is a linear combination of F's. Right? And in particular, there's one more thing that's going to change. It's going to stop at M. Okay, so let's write it. T of E1 is now an element in W. An element in W is a linear combination of F1 through Fm. So it's some A11 F1 plus some A21 F2 plus dot 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 some A M1 Fm. Do you agree? Any element in the range is a linear combination of the basis for the range. Okay? And likewise, T of E2 is A12 F2 plus A22 F1, sorry. A12 F1 plus A22 F2 plus A M2 Fm. Okay, so the first coordinate, the first index of A stands for which F is it a coefficient of. The second index stands for which E was it a T of. Okay, bless you. See? That's a good way to save somebody from sneezing. Okay, so here it's going to end up at a mn, and there's a dot, dot, dot. Here it's a1n f1, a2n f2, all the way up to a mn fm. Do you agree? Good? Take the transpose of the coefficient matrix, which is this, and the matrix you get which now the only thing I have to change is the bottom row. The bottom row, which is now the last column, ends with row M. A M1, A M2, dot, 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 A M N. And this satisfies that it's the representing matrix of the transformation T with respect to these two chosen bases. Good? So you can trace back to what we did in the example and see that this is precisely what we did in the example. Good? Everybody with me? Okay. Now there's a theorem here. There's a theorem. I just presented it as an algorithm. I told you, hey, this is what you do. That's not a way of proving things, right? By saying, hey, this is what you do. Okay? So the statement is that if you do this, if you follow this procedure, if you take a linear transformation, choose a basis for the domain space V, choose a basis for the range space W, do T to all the basis elements in E, spell them out as linear combinations as basis elements of W, take the transpose of the coefficients. All we did so far was say what to do, and then there's a theorem. The theorem is not just then this satisfies this, then the theorem is, so this is in fact the theorem. Let me write it on this board and then we'll duplicate it on separately. Theorem, if you do all of this, then what you get satisfies T, E, F multiplied by V, E equals T of V, F. This is a theorem. So the full formulation of the theorem starts with this word and ends with, instead of then A satisfies this, then A satisfies this. That's the theorem. Okay? And it requires proof. And proving it is a bit of a nuisance. It's not long. It's not long. It's just a bunch of index work that really does precisely what we did in the examples and shows that you get the same thing. So you have to decipher what this means. What are the columns of this? The columns of this are these. And decipher what, and multiply it by V, represented in the basis E. And see that you get is precisely what you get when you multiply T of, when you write the coefficient vector of T of V with respect to the basis F. Okay, so T of V, V is alpha 1, E1 up to alpha n plus dot 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 plus alpha n En, right? So T of V is a linear combination of these guys, so it's a linear combination of these guys, and you get the same thing. Okay? But I'm not going to go through the trouble of writing out all the details because it's just tracing indices. And as I said before, there's not much to benefit from actually spelling out the proof of this theorem. Okay? It's good practice if you want to see that you're not scared of indices, but that's all there is to it. Okay? So I'm not going to prove this, but it is important to remember the algorithm to understand via the example why it works, okay? Why it does precisely what we want, okay? And to understand this statement, not to freak out when you see this written, but to understand what it stands for. Okay? Questions?
I have a question, but it's not really...
Ask. It's a good question.
We usually use the standard basis when we're choosing
Right.
a basis for something.
Right.
Is there anything that...
Is there any reason in the world, to ever use a basis other than the standard basis? That's a great question.
It's not all the space.
No. E is a basis for V, for the entire space. Why not choose a different basis? Or why choose a different basis? Why not work with the standard one? Isn't it nice and friendly and easy to work with? That's a great question. And that's an entire topic that's going to be our next topic. But I can tell you the answer. I can give you a spoiler and tell you the answer in brief. Okay? What we do when we choose a basis, given a linear transformation, we choose a basis, we produce a matrix, this matrix. Okay? Let's go back to the example. We produce this matrix. Okay? This is a pretty nasty matrix. It only has 1 0. Okay? In this case, it's a 3 by 4 matrix, so that's not such a big deal. But suppose you really have a linear transformation between a 257-dimensional space to a 4,524-dimensional space, and you want your computer to do stuff with it, okay, to calculate stuff. You want to produce this matrix representation, and then all you have to tell the computer is multiply the matrix times these vectors, and there you have it, right? If you can somehow produce this matrix, not to be just anything, but to have, let's say, many, 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 many zeros in it, the computer is going to work a lot less, okay? So your goal is, and that's what we're heading to, we don't just want to do this, take the standard basis, find the representing matrix with respect to that, because that doesn't give you a lot of control. It just produces a matrix, and whatever you got is what you got. We want to choose somehow the bases wisely to produce the representing matrices to be very easy to work with. For example, have a lot of zeros and ones. And that's when we're going to say, okay, we're going to compromise. We're not going to choose the standard basis. We're going to choose a different basis. And we saw different bases for different spaces. But the benefit is going to be that we're going to have very nice looking matrices. And it's going to be a topic. We're going to say, when can we guarantee that the matrix that we get, for example, is a diagonal one? That's like the nicest thing possible. And if it's not diagonal, maybe it will be almost diagonal and have just here and there some non-zero off-diagonal entries. Okay? And that's a whole topic that we're going to discuss. Okay? And there's going to be terminology there and so on and so forth. We're not there yet, but that was a great question. I'm very happy that you asked it.
So
okay?
This one is not an optimal one, right? That's what you meant. Right?
It's not optimal in the sense that maybe choosing a different basis would produce a T, and it's not going to be E and F. It's going to be S and R. A different bases would produce a matrix here that would have 1, 1, 1, and all the rest zeros. Maybe. Okay? So we don't know that yet. We don't know how to control for what matrices do we get. Okay? There's a lot of stuff we still have to discuss. The semester is not over yet. There's still a month to go. Okay? But that's a big goal. Okay? And that's going to depend on the flexibility that we have is precisely in choosing different bases. Good? Okay, so this wraps up this discussion. I hope this is the bottom line. Okay, so this is the theorem, but the bottom line is also how we do it. And I hope you got the idea. So what we want to do next, is the following. So there's a relation between matrices and linear transformations. It's not a very vague relation. It's very precise. Given a linear transformation, I know how to produce a matrix. Given a matrix, I know how to produce a linear transformation, right? So it goes both ways. Matrices and linear transformations are two ways of looking at the same thing, in fact. Okay? So on matrices, we have a bunch of operations. We know how to add matrices. We know how to multiply a matrix by a scalar. We know how to multiply matrices, right? We have inverse matrices. There's a lot of stuff going on there. That stuff should translate to linear transformations, right? Operations on linear transformations. How do we multiply linear transformations? What does it stand for? How do we add linear transformations? What does it stand for? And once we define all of that, operations on linear transformations, once we define them, how do they relate to going back and forth between linear transformations and matrices. And the statement is going to be that they go precisely back and forth. Add the linear transformations. Go to the matrix side using this procedure, or go to the matrix side and then add, you get the same thing. Okay? Multiply and go, or go and then multiply, you get the same thing. Okay? So we have to define what are operations on linear transformations, and then show that they exactly correspond to the equivalent operations on matrices. Good? So that's where we're heading.